Good morning, everyone. This is an audio recording for visually impaired student. Today I am going to read a chapter from Pradeep's Inorganic Chemistry written by Dr. K. Basin. Chapter Hard and Soft Acid and Bases. The term acid and bases are routinely used in our daily life. Chemists have been classifying substances as acid and bases since long time. Lavoisier noticed that the common element in all acids are oxygen. The word oxygen in Greek means acid former. However, Humphrey showed later that all the acids contain hydrogen. It was in 1884 Arrhenius, a Swedish chemist, developed the theory of acids and bases, known today popularly as Arrhenius theory of acid and bases. According to Arrhenius, an acid is a substance which gives hydrogen ion in aqueous solution, and a base is a substance which gives hydroxyl ion in aqueous solution. The strength of an acid or a base depend upon its capacity to provide H positive and OH negative ion respectively. The process of neutralization of an acid by a base can be represented by a reaction. H positive plus OH negative give H2O. In 1923, G. N. Bronsted in Denmark and T. M. Lovney independently proposed a new acid-base theory. According to their theory, an acid is a proton donor, whereas a base is a proton acceptor. The acid-base reaction is regarded as a proton transfer reaction. In 1923, G. N. Lewis gave another general definition of acid and a base behavior in terms of electron pair donation and acceptance. However, this theory got the recognition only in 1938. According to Lewis, an acid is a substance which can accept a pair of electrons, while a base is a substance which can donate a pair of electrons. In other words, an acid is an electron pair acceptor while a base is an electron pair donor. The earlier definition of acid and bases were solely based upon the observable property such as taste, ability to dissolve substances insoluble in water, and their effect on vegetable dyes. The term acid was applied to substances which have a sharp or a sour taste, turn blue litmus red, react with certain metals to liberate hydrogen gas, and have the ability to dissolve substances insoluble in water. On the other hand, the term base was applied to substances that have a bitter taste, soapy feel, turn red litmus blue. However, testing and filling chemicals are dangerous method of determining whether the substance is an acid or a base. You should never ever taste or touch solution of chemical in laboratory. There are, however, other methods of recognizing acid and bases. For example, acid and bases change the color of certain dyes, known popularly as indicator. One of the most common indicator is a vegetable dye obtained from the lichen known as litmus. Aqueous solution of acid turn the litmus red, whereas aqueous solution of bases turn it blue. Thus, any substance which has an unshared pair of electron can act as a Lewis base, whereas a substance which have an empty orbital to accommodate a pair of electron act as a Lewis acid. In other words, substances capable of donating a pair of electrons are regarded as Lewis base, and the substance capable of accepting a pair of electrons are regarded as a Lewis acid. Acid base or neutralization reaction may thus be regarded as a donor Lewis base, acceptor Lewis acid reaction, or a coordinate covalent bond formation reaction. The classical example of Lewis acid base reaction is that of the between boron trifluoride and ammonia. Using electron dot diagram, we can see that boron trifluoride is a Lewis acid and ammonia is a Lewis base. Ammonia plus BF3, it will give NH3BF3, donor acceptor or a coordinate bond formation reaction. Lewis concept of acid and bases is very commonly used because of its simplicity and the easy with which the formation of coordination compounds can be explained. In brief, all the usual ligands can be regarded as a Lewis basis, whereas all the metal ion can be regarded as a Lewis acid. The degree of affinity of a metal ion for ligand can be termed as a Lewis acidity, and the tendency of a ligand to combine with the metal ion can be regarded as a Lewis basicity. Hard and soft acid and bases. An acid-base reaction according to Lewis concept involves the reaction between a donor A and acceptor B as to form a complex as given below. A plus B with lone pair, it will give AB. The formation of the stable complex between the donor A and the acceptor B depend upon the nature of the species A and B involved. It has been since long that certain ligands form more stable complexes with metal ions such as Ag positive, Ag2 positive, Pd2 positive, and Pt2 positive. On the other hand, certain ligands form stable complexes with metal ions such as Al3 positive, CO3 positive, Pt4 positive. Based upon the prefictional bonding, the acid and bases have been classified into two groups, Group A and Group B according to their preference. Class A metal ion include alkali metals, alkaline earth metals, lighter and more highly charged ion, for example Ti4 positive, Cr3 positive, Al3 positive, Fe3 positive, CO3 positive, etc. Hydrogen ion as H positive. Class B metal and include heavier transition metal of second and third transition series like CD2 positive, Ag2 positive, PD2 positive, PT2 positive. Heavier transition metal in lower oxidation state is Ag positive, Hg2 2 positive, Cu positive. Low valent metal ions such as a zero valent metal in metal carbonyls. Depending upon the type of metal ion, ligand can be classified at class A or class B depending upon their preference. Class A ligand include molecules or ion with donor atom and nitrogen, oxygen, fluorine, chlorine, etc. It is important to note that class A ligand prefer to form strong complex with class A metals. Class B ligand included molecules or ion with donor atom PAS, SSEI, etc. Class B ligand preferred to form complex with class B metal ion. It was in 1963 Pearson coined the term hardened acid bases and base for class A and class B metal ion and ligands respectively. According class A metal are preferred to hard acids while the class B metal ion are called soft acids. Similarly, class A ligands are called hard bases whereas class B ligands are termed as a soft bases. In summary, according to Pearson, class A acids are hard acids like H positive, Li positive, Na positive, Be2 positive, Mg2 positive, Cr3 positive, Fe3 positive, etc. Class B acids are soft acids Ag positive, Pd2 positive, copper positive, platinum 2 positive. Class A bases are hard bases H2O, NH3, F negative, ROH, etc. Class B bases are soft bases R3P, R3AS, R2S, R2SC, I negative, SCN negative, etc. Classification of acid and bases as hard acid and soft. Pearson observed that it is possible to correlate acid base interaction on the basis of hard and soft acid and bases. He observed that the type A metal ion, that is, acids were small, compact, and not very polarizable, and thus preferred ligand bases that were also small and less polarizable. He called these acids and bases as hard. On the other hand, the type B metal ion and the ligand they prefer appear to be large in size, more polarizable. He described these acids and bases are soft. Pearson generalized the acid base relationship and expressed that hard acid preferred hard bases and soft acid prefer soft bases. Classification of acid. The general classification of some common hard acid and bases along with some borderline cases is given in table 4.1. Hard acids are cation of smaller size or lighter element. Hard acids are cation of the higher oxidation state. Hard acid are molecules cation with lesser number of valence electron. Hard acid hold the valence electron tightly and consecutively are not easily polarizable. In summary, hard acid binds strongly to a proton. Hard acids are small size, compact, and are not easily polarized. A close look at table 4.1 also reveals that soft acid possesses the following characteristics. Soft acids are cation of the larger size or heavier elements. Soft acids are cation of lower charge. Soft acids are molecule or ion with larger number of valence electron. Soft acids do not hold the valence electron tightly and are therefore easily polarizable. In summary, soft acids are large sized and easy polarizable ion or a molecule that bind strongly to highly polarizable ion or molecule. It is important to note that there is no sharp division between acid and soft acids. There are a number of Lewis acids that are neither too hard nor too soft acids. Such type of acids that are neither hard or not soft are called the borderline acids, which are shown on the extreme right of the table 4.1. Borderline acids have property which are intermediate between a hard acid and a hard base. In case of borderline acid, the properties such as size, oxidation state, and polarizability of the cation or molecule are neither too low nor too high. On the other hand, soft acids will show the opposite trends and the following order of preference for binding the donor atom or ion within a group is observed. The above trend can be pictorially represented as complex of type A metal, ligand complex of type B metal. Simple. Question 4.1. What type of interaction do you accept between a hard acid and a hard base? Answer. Since both hard acid and hard bases are not easily polarizable, their interactions are predominantly ionic. What type of interaction do you expect between a soft acid and a soft base? Since both soft acid and a soft base are usually polarizable, the interaction between them are predominantly covalent. Classification of bases. A general classification of some commonly ligands into hard or a soft bases along with the borderline bases is presented in table 4.2. A glance at the table 4.2 reveals some of the important characteristics of hard bases. Hard bases bind strongly to the proton. They contain donor atom of high electronegativity. The donor atom in hard bases possesses low polarizability. They are not easily oxidized. Hard bases contain empty orbital of higher energy. In summary, hard bases bind strongly to a proton. The donor atom, in case of hard bases, is of high electronegativity and of low polarizability. A further inspection of table 4.2 reveals that the following features are observed in case of the soft bases. Soft bases contain donor atom of low electronegativity. They contain donor atom of higher polarizability. They get easily oxidized. They are associated with empty low lining energy orbitals. In brief, soft bases contain less electronegative non-metal included carbon, sulfur, phosphorus and iodine. The donor atom in such bases possesses donor atom that are easily polarized. Just as there are borderline acids, there are borderline bases also. The property of borderline bases are in between those of the soft and hard bases. It is important to note that the categories are not rigidly divided. For example, the halide ion from a series from a very hard fluoride ion through a hard borderline chloride ion to the borderline bromide ion and the soft iodide ion. The soft acids, also known as a class B metal ion, are the group of the metal ion that are in lower right position of the metallic element as shown in figure 4.1. Pearson HSB principle. Pearson proposed a simple rule for predicting the stability of coordination compound formed between an acid and base. This rule is quite often named as HSAB principle. According to Pearson HSAB principle, hard acid prefer to bond with hard bases while soft acid prefer to bond with soft bases. It is important to note that hardness and softness of acid and bases refer only to hard and soft interaction. It is by no means related to the strength of acid and bases. For example, both F negative and OH negative ions are hard bases, but the basic strength of OH negative ion is approximately 10 to the power 13 times that of the fluoride ion. In other words, hard acids will show the following order of preference of binding the donor atom or ion within a group. F negative more than chlorine, more than bromine, more than iodine. R2O more than R2S, more than R2SC, more than R2T. R3N is more than R3P, more than R3S, more than R3SB. Application of HSB principle. Pearson principle of HSB has a number of applications in inorganic chemistry. Some of these are discussed below. First, stability of the complexes. We have already noted that hardness and softness of acid and bases are related only to the hard and the soft interaction. Hardness and softness of acid and bases has nothing to do with the inherent acid or basic strength of an acid or bases. For example, both OH negative and F negative ions are hard bases, although OH negative ion is 4 stronger as base than F negative ion. In fact, OH negative ion is 10 to the power 13 times more stronger as base than E negative ion. However, in HSAB principle, both OH negative and F negative ion are at pair with each other. Pearson in 1963 explained the relative stability of coordination complex on the basis of HSAB principle. Let us consider a general reaction between a Lewis acid and a Lewis base. A plus B, it will give AB complex. The complex AB will be more stable if A and B are either both hard or both soft. The complex AB will be less stable if A is hard or B is soft, or A is soft or B is hard. For example, complex between a soft acid Ag positive and soft base I negative is quite stable, in contrast to one between a soft acid Ag positive and a hard base F negative. Ag positive plus 2I negative, it will give AgI2 negative, stable complex, soft interaction. Ag positive plus 2F negative, it will give AgF2 negative, unstable complex, soft hard interaction. Similarly, the reaction between LiI and CSF resulting in the formation of LiF and CSI constitute an interesting example suggesting the professional stability of soft and hard combination. Li soft plus CSF soft hard, it will give LiF hard plus CSI soft. Some of the important reactions suggesting the stability of the soft and hard interaction are given below. CuI plus CuF, it will give CuF2 plus 2 CuI. CaS plus H2O, it will give CaO hard plus H2S soft. BEI hard soft plus Hg F2 soft hard, it will give BeF2 hard plus Hgi2 soft. The rule of thumb in determining the stability of the complex is the professional combination of hard and soft interaction. Why COF63 negative complex is more stable than COI63 negative. In both the complexes, the coordination state of cobalt is 3 positive. CO3 positive is a hard acid. Therefore, its combination with a hard base, that is F negative, will lead to COF63 negative, which is harder interaction. On the other hand, the combination of CO3 positive with a soft base I negative will lead to COI63 negative, which is hard soft interaction. Thus, COF63 negative is more stable than COI63 negative. It has also been noted that the combination of hard or soft ligand with a metal ion is always preferred over the combination of a mixture of hard and soft ligands with metal ion. For example, the complex COCN5 3 negative and CONH3 5F2 negative are far more stable, whereas the complex COCN5 F3 negative and CONH3 5 I3 positive are unstable. This is because Cn negative and I negative are both soft bases, whereas ammonia and F negative are both hard bases. Second, classification of acid and bases. The acid and bases can be classified as hard or soft depending upon their professional or hard and soft reactant. Let us consider the following reaction. BH positive plus CH3Hg positive. It will give CH3HgB positive plus H positive ion. We have already know that H positive is a hard acid, whereas CH3Hg positive is a soft acid. If B happen to be a hard basis like ammonia, the reaction on the left hand side will be preferred. NH4 positive plus CH3Hg positive will formed from CH3H positive ammonia plus H positive. Conceptually, ammonia can be written as NH4. It will give NH3 hard base plus H hard acid, which means the formation of NH4 positive is preferred because of the hard acid and a hard base. On the other hand, if B is a soft base like R2S, the right hand side reaction will be favored as shown. R2SH positive plus CH3Hg positive, it will give CH3Hg SR2 plus H positive ion. Conceptually, CH3HgSr2 positive can be written as CH3HgCsR2 positive. It will give CH3Hg positive plus Sr2, which means the formation of CH3HgSr2 is preferred because of the soft acid and a soft base. Similarly, an acid A can be preferred as hard or soft depending upon the direction of equilibrium. AF plus SCN negative, it will give ASCN plus F negative. We know F negative is a hard base and SCN negative is a soft base. If A is a soft acid like Hg positive ion, then the above reaction in a forward direction is favored. AgF plus SCN negative, it will give AgSCN plus F negative. Conceptually, AgSCN is formed through soft-soft interaction and hence according to HSB theory, the reaction is preferred in a forward direction. On the other hand, if A happen to be hard acid, then the forward reaction is not favorable, rather than the backward reaction is preferred. NaSCN plus F negative, it will give SCN plus NaF. Conceptually, NaF is formed through harder interaction. Thus, according to HSAB theory, the reaction is preferred in a backward direction. OH negative is much stronger base than SO32 negative and hence cannot be displayed by weaker bases SO32 negative. These reaction, however, is favorable by HSB principle. CH3CdOH plus SO32 negative, it will give CH3CdSO3 negative plus OH negative. It is important to conclude at this stage that Lewis acid Lewis base reaction are governed by two independent principles. First is the strength of acid or base, second softness and hardness of acid or base. The definition of hardness primarily uses the idea of polarizability, which states that a less polarizable species is hard and a more easy polarized is soft. For ion of similar charges, the ratio of charge to radius should use to assess the relative polarizability or relative hardness or softness. However, HSAB principle does not take into consideration the quantitative idea of relative hardness or softness of the spaces. In summary, the major limitation of HSAB principle are: HSAB principle is too general and without any qualitative scale of measurement. It does not take into consideration the acidic or basic strength of the component. It fails to explain the feasibility of the reaction. CH3 positive plus H2, it will give CH4 plus H positive, Del H is equal to 86 calorie per mole in spite of soft CH3 positive H negative interaction. It is probably the greater acidity of proton H positive related to CH3 positive cation that is responsible for the unfavorable reaction. Limitation of HSAB principle. The hardness and softness of an acid or a base is primarily related to the stability of hard and the soft interaction. It has no concern with the acidity or basicity of the acid or bases. For example, OH negative and F negative are well known hard bases. However, the basicity of hydroxide ion OH negative is very large as compared to the fluoride ion. In fact, the basicity of hydroxide ion pK is equal to 15.7 is 10 की power 13 times that of the fluoride ion pK value is equal to 2.85. A strong acid or a strong base is well known to display a weak acid or a weak base. For example, the reaction between a sulfide ion and the hydrogen fluoride proceed in a forward direction. It means that the stronger bases SO32 negative can be easily displace the weaker bases F negative form the acid hydrogen fluoride SO32 negative plus HF. It will give HSO4 HSO3 negative plus F negative. Equilibrium value is equal to 10 ki power 14. However, the above reaction is not favored according to HSAB principle as detailed below. SO32 negative plus HF, it will give HSO3 negative plus F negative, which only favor hard and soft interaction. Similarly, a very strong base OH negative can display a weak base, form a soft acid methyl mercury second cation OH negative plus CH3 HgSO3 negative. It will give CH3 HgOH plus SO3 2 negative. K value is equal to 10. However, the above reaction is also not favored according to HSAB principle, which only favor harded or soft interaction. In both above cases, it is inherent strength of bases SO32 negative is more fluorine and OH negative is more than SO32 negative. That forces the reaction in the forward direction in spite of less preferred formation of hard soft pair in the product. This is true in case especially when the inherent strength of the bases being compared are significantly different. The order of the basic strength being OH negative is more, SO32 negative is more, F negative. In other words, significant different basic strength forces the reaction against the basis of hard soft interaction. However, when both the strength of an acid and basis and hardness and softness are not significantly different from, then HSB principle work while resulting in product having hard and soft combination. For example, CH3 HgF soft hard plus HSO3 negative hard soft. It will give CH3 HgSO3 negative soft plus HH hard interaction. K value is equal to 10 ki power 13 3 and CH3HgOH soft hard plus HSO3 negative hard soft. It will give CH3HgSO3 soft plus HOH hard. K value is equal to 10 ki power 7. It is important to mention that inherent strength of acid and bases should not be ignored while applying HSAB principle. Symbiosis. The hardness or softness of an acid or basic center is not an inherent property of an atom, but depending upon the substituent. Thus, ammonia is a hard basis while pyridine is a borderline base. The acidic B3 positive ion is a borderline between a hard and a soft acid. Addition of the three small size non-polarizable substituent like fluoride ion make it a hard Lewis acid, whereas the addition of electron donor and easily polarizable group like hydrate ion make it is a soft Lewis acid BH3. The difference in the hardness and softness of BF3 and BH3 can be illustrated nicely in the following example. R2S BF3 soft hard plus R2O hard It will give R2O dot BF3 hard plus R2S soft. R2O dot BH3 hard soft plus R2S is soft. It will give R2S dot BH3 soft soft plus R2O hard. Jorgensen in 1968 observed that hard ligands have a tendency to combine with a metal ion having hard ligand and a soft ligand having a tendency to combine with the metal ion already having soft ligand. He coined a term symbiosis for such interaction. The hard BF negative molecule prefer to combine with the hard base F negative to form tetrafluoride fluoroborate BF4 negative, whereas soft acid BH3 prefer to combine with soft base H negative ion to give tetrahydroborate BF4 negative ion. BF3 hard acid plus F negative hard base, it will give BF4 negative, or B2H6 plus 2H negative, it will give 2BH4 negative. An important outcome of symbiosis is that symmetrical substituent compounds are formed in preference to the unsymmetrical substituted compound. For example, compounds containing mixed substituent interact strongly to yield symmetrical compound with the same substituent as given below. BH3F negative plus BF3H negative. It will give BH4 negative soft salt plus BF4 negative hard hard. Similarly, mixed fluoride methane give to symmetrical methanes. CH3F soft hard plus CF3H hard soft, it will give CH4 soft salt plus CF4 hard hard. In brief, symbiosis may be defined as a tendency of soft ligand to combine with metal ion already having soft ligand and the tendency of hard ligand to combine with a metal ion already having hard ligands. Theoretical basis of hardness and softness HSB principle. A number of theories have been proposed to explain the preference of hard acid toward hard bases and a soft acid toward bases. First, electrostatic interaction theory. According to this theory, hard acid and a hard base form purely ionic compound. Therefore, hardened interaction are purely ionic or electrostatic. Most of the hard acids such as Li positive, Na positive, K positive, etc. and hard bases such as O2 negative, F negative and OH negative ion are well known to form ionic compound. We know that the electrostatic energy of a lone pair is inversely proportional to the interatom distance. It means smaller the ion, the smaller will be the internuclear distance and hence greater will be the electrostatic energy between the ions. As a result, the final compound formed by hard acid and a hard bases will be highly stable. Second, polarizing power and polarizability. Electrostatic interaction cannot explain the soft interaction because of the bigger size of soft ion. Therefore, the interaction between the large size acid and base must involve covalent character. For example, soft acids such as Ag positive, Hg positive, Cu positive, etc. form strong compound with soft bases like S2 negative, I negative, which have substantially covalent character. Almost all the soft acids have 6 or more d electrons. Soft acid with d10 configuration are excellently soft acids. For example, Ag positive, Hg2 positive. It is these d electrons that have more polarizing power. Secondly, the soft bases like S2 negative and I negative are easily polarizable. Thus, bonding between soft acid and soft bases is largely covalent. Third, natural occurrence of ore and minerals. The natural occurrence of ore of the certain metals can be explained on the basis of HSAB principle. Hard acid metal ions such as Mg2 positive, Ca2 positive, Al3 positive, Fe3 positive, Cr3 positive, etc. frequently occur as their oxide, fluoride, chloride, and carbonates. This is primarily due to their preferred hard acid hard base interaction. We know that oxide O2 negative halide F negative or Cl negative and carbonate CO3 2 negative are all hard bases. These hard acid metal ion cannot occur as a sulfides S2 negative because S2 negative is a soft base and cannot form stable compound. On the other hand, the soft metal ions such as copper, Ag positive, Cd2 positive, Hg2 positive, Pd2 positive occur invariable in ore as their sulfide due to soft acid soft base interaction that result in the formation of stable complex. Interestingly, the borderline acids like CO2 positive, Ni2 positive, Pb2 positive, Zn2 positive can occur both as a sulfide as well as their oxides or carbonates as a result of their intermediate character. Fourth, catalytic poisoning. All metal atom in zero oxidation state are soft acids. Some of the metal name vanadium, chromium, nickel, palladium, etc. are well-known catalysts. These metal catalysts have been found to be easily poisoned by soft bases, carbon monoxide, unsaturated hydrocarbons, olefins, alkynes, dienes, and arenes, organophosphines R3P and organoarenes R3AS, etc. This poisoning is attributed to the soft acid soft base interaction between the metal atom and the soft ligand. In fact, these soft ligands are absorbed strongly on the surface of the metal and the block the reactive site by forming metal complex. In other words, the metal atom lose their reactivity and are said to be poisoned. The soft base complex with the metal in atomic state will act as a poison toward metal catalyst. Electronegativity and hardness and softness. Hardness and softness are related to electronegativity. Species with higher electronegativity values are assigned greater hardness, and those with lower electronegativity value are assigned greater softness. Electronegativity conventionally means the power of an atom in a molecule to attract electron toward itself. However, in these cases, it refers to the power of an individual ion participating in a reaction. For example, lithium atom is known as highly electropositive or lowly electronegative metal, but the cationic spaces allied positive which have high second ionization potential have a greater tendency to attract electron toward itself. As a result, allied positive is considered to be more electronegative and hence is a hard acid. On the other hand, heavier transition metal ion in a low oxidation state like Cu positive, Ag positive, Hg positive, Cd positive have relative low second ionization potential and consequently possesses low value of electronegativity. As a result, these ions are considered as soft acids. Using the same concept of electronegativity, we can define hard acid and a basis. These relationship between the hardness and electronegativity can explain several important features as to why trifluoromethyl group is a harder compared to methyl group. Second, boron trifluoride is harder compared to boron. Third, ammonia is harder than trimethylamine. Fourth, trifluorophosphine is harder than phosphine, which in turn is harder than trimethylphosphine. Mulkin-Jeff defined electronegativity as a linear function of the partial charge developed on a metal according to Xi is equal to A plus B del. A is equal to electronegativity of the atom. B is equal to the rate of change of electronegativity with charge. The electronegativity value A of the atom is similar to of that of Pauline or Alred-Rochow, and the parameter B is called the charge coefficient. Small hard and non-polarizable atom have higher value of B, whereas the larger soft and polarizable atom have small value of B. Parr and Pearson introduced a new term called absolute hardness for neutral as well as charged spaces and correlate with the absolute electronegativity. The absolute hardness is defined as one half the difference between the ionization energy and electroaffinity. Absolute hardness is equal to I minus A upon 2. I is equal to ionization energy, A is equal to electron affinity of the species in question. We know Mulkin definition of electronegativity. Psi is equal to I plus A upon 2. The hardness of base B and acid A may be given. NB is equal to N species B positive is equal to half IB positive minus AB positive. Na is equal to half Ia minus AA. In order to understand as why in this question 4.6 the base B is represented as B positive, whereas in equation 4.6 the acid A is represented as such as A. Let us consider the interaction of acid A and base B to form the compound AB. A plus B, it will form AB. A acquire partial negative and B acquire the partial positive. In the formation of compound AB, the electron will move from B to A, which is indicated by the partial positive and negative charge. Hardness of B refer to the species going from partial positive to a charge 1 positive on ionization, while hardness of A refer to the species on ionization from partial negative to a charge 1 del negative. If the shift of the charge del is taken as equal to 0.5, then a charge on B become 1 plus 0.5 is equal to 1.5, and on A becoming 1 plus minus 0.5 is equal to 0.5. Thus the charge on B changes from 0.5 to 1.5 with an average of half. 0.5 plus 1.5 is equal to 1, and that on A changes from minus 0.5 to 0.5 with average is equal to 0. This justifies the reason why the species B is shown as B positive and A as neutral in equation 4.6 and 4.7. A close inspection of table 4.4 and 4.5 reveals that the absolute hardness values are in good agreement with their non-chemical behavior. Hydrogen is the only exception which is different in all the three tables. It is advisable to consider as a special cases. With the exception of H negative, the value of hardness parameter of all the bases are as expected. The hard bases F negative and OH negative have larger value of Nb, while the soft bases SH negative and CH3 negative have smaller values. The hard acids such as Na positive, Mg2 positive, Al3 positive have large Na value, whereas the soft acids such as Hg positive, Cu positive will have small Na value. Borderline metal ions such as Mn2 positive, Fe2 positive, Na2 positive, Cu2 positive, and Zn2 positive have intermediate value. It is interesting to note that down a column in a periodic table from Mg2 positive to Ba2 positive, there is a steady increase in the softness. Similarly, observation of softness is made in going from Ni2 positive to Pd2 positive. This is also an accepted increases in hardness value with increase in oxidation state as. However, there are certain discrepancy as well. For example, Ti positive value 7.2, Ti 3 positive 10.5. The Na value of Tl3 positive suggested it with a harder acid, whereas Tl3 positive is well known to be the chemically softer. However, a comparison of Tl3 positive with other trivalent ion show the expected soft character. Soft acids are generally transition metal in low oxidation state containing loosely held d or electrons. These electrons can be easily donated to the ligand. On the other hand, the soft bases are pi bond acceptors such as CO phosphanes, alkene and alkynes. In soft acid base interaction, pi bonding is very important. Sigma bond formation due to the donation of electron from the base to the metal is reinforced by the pi bond donation from the metal to the base. Relation to molecular orbital theory. Molecular orbital theory is a powerful tool for explaining the structure and bonding, visible UV spectra, and detailed mechanism of chemical reaction. The concept of absolute electronegativity and hardness can be explained using molecular orbital theory. The ionization energy is a measure of energy of the highest occupied molecular orbital, that is HOMO, whereas the electron affinity is a measure of the energy of the lowest unoccupied molecular orbital, LUMO, with change in sign for a given molecule. According to
Koopman theory, EHOMO is equal to minus I, ELUMO is equal to minus EA. The hardness and softness depending upon the average gap between the HOMO and LUMO. The combination of soft acid with soft base is analogous to the situation in which LUMO of the Lewis acid has about the same energy as the HOMO of the Lewis base. The combination of orbital resulting in greatly reduced energy for the electron pair coming from the base as shown in figure 4.2, thus giving a strong covalent bond. For the hard acid and a hard base, there is a greater mismatch of LUMO and HOMO energy so that there is a little energy advantage to be gained from the orbital interaction. Thus orbital bonding will not occur to any significant extent and an ionic interaction will result instead. Thank you.